So good morning, good afternoon, good evening, depends on where you are in the world. So today we are here for another very interesting CASS talk that will be done by Professor Maksim Jenihhin from Tallin University of Technology in Estonia. So, we have the pleasure also here to have a Professor Sergio Bampi that will be the session chair. But before giving the floor to Sergio to do the introduction of Professor Maksim, just some announcements. So if you lost some of the CASS talks being done since 2020, you have more than 150 talks available in this YouTube channel, so for free. So if you didn't see all the talks, you can go there and go there now to hit this YouTube channel and to see the other ones. Also, this year we have the 10 IEEE World Forum of Internet of Things that will be in November in Ottawa, Canada. And the paper submission extended deadline is May 15th. So you have about 2 weeks to finish your paper. And it's important that the Security and System Society community that is part of the IEEE IoT Technical Committee to have a good participation in the conference. So we also would like to welcome all you to prepare your papers for next edition of LASCA, so the flagship conference of IEEE Security and System Society in Latin America. That means an international conference of CASS in the region. And as you should know also, best papers are invited to submit extended versions to TCAS 2 and TCAS 1. The ones that are included in TCAS 2, they appear in the months of the conference. So it's a very short path to. And next year it will be in south of Brazil, in the most traditional wine region that is close to Porto Alegre. So it's very easy to reach. And I could give a lot of extra reasons to go there, but I don't have time for this. And 2026, it will be in Arequipa, a wonderful location in Peru also. And 2027 will be also in Panama City. That is another very interesting destination. Also, another CASS event in South America is the SBCCI. So this will be done in João Pessoa in the northeast of Brazil this year. So the paper submission deadline is already closed, but you can prepare your papers for the 2025 edition. That will be an edition of Chip in the Jungle. So it was organized one edition in year 2000. So now 2025, 25 years after, we go back to Manaus. So the gateway to the jungle. So it will be a very nice experience. And you have plenty of time to prepare your papers to submit it to this special edition. Also, next week, we have our traditional microelectronics school and South Symposium Microelectronics in the south of Brazil, where we are celebrating 40 years of the symposium and 25 years of the microelectronics school. So it will be in the city of Bagé, that is about 500 kilometers from Porto Alegre. But this year we are celebrating 75 years of CASS. So as a big promotion, if you are not yet a member of CASS Society, you can become a member for free, not only student member, but professional one. So it's a great opportunity to join the CASS Society. But we are here today to attend the talk by Professor Maksim Jenihhin, and Professor Sergio Bampi is the session chair. So Bampi, the floor is with you to do the presentation of Maksim.
Okay, thanks a lot, Ricardo. And, we'd like to thank
the session chair and also to Maksim to accept the invitation to give the talk today. Thanks.
Okay, thanks, Maksim, for being our distinguished speaker today. Okay, we are very pleased on behalf of the Rio Grande do Sul chapter of Circuits and Systems Society. very pleased to have your talk. We will be talking about cost-efficient reliability for edge AI chips. A few words about our speakers. Professor Maksim Jenihhin is a tenured associate professor of computing systems working on reliability of circuits and systems. He's the head of the research group on trustworthy and efficient computing hardware at the Tallin University of Technology, which is in Estonia. He has published more than 150 papers and served on executive committees and program committees for numerous IEEE conferences like DATES, European Test Symposium, Latin American Test Symposium, and others. Professor Jenihhin, our speaker today, coordinates national and European collaborative research projects about energy efficiency and reliability of edge chips, in particular targeting AI applications, and also cross-layer self-health awareness of autonomous systems. With no further ado, it's been taking too much long. Thanks a lot, Professor Maxime, and the floor is yours for this very interesting talk. Thanks a lot.
Thank you, Sergio, and thank you, Ricardo. So I really appreciate this opportunity. I was following numerous talks by the chapter of Rio Grande do Sul, and now it's really an honor to be on the other side of the screen and to present some results that we have achieved in our group. So I would like to start this talk with a compliment to Patrick Grönenveld, who also performed in one of these CASS talks just several months ago. And earlier last year, in 2023, he actually posed a very interesting question. How many transistors are alive in the world? And he also gave an exciting answer. So he claims that there are approximately as many transistors as grains of sand on all beaches in the world. And this claim comes along with very nice computations and calculations. So there is a set of quite trustworthy assumptions about the size of the sand grains and the size of the beaches in the world, etc., etc. And if we multiply all the numbers, then we'll get 6 trillion as the number of grains of sand on all beaches. And then another calculation, considering the number of wafers being produced annually and the number of transistors located on each wafer, and then the lifetime approximate for each chip, actually we get the same number. We also get 6 trillion as a number of transistors which are actually running, which are alive as of now, actually as of last year. So I believe that this year we should have even more transistors. So it's a really exciting comparison, and I really appreciate it. So what can be more exciting is actually to follow the trends of AI, artificial intelligence development, and in the previous several years, it has outperformed human already in numerous disciplines, in numerous domains, and keeps conquering new areas every year. Among the recent trends for AI development is move of AI towards the edge, towards the source of the data, closer to the sensors, and that allows to enable numerous new applications, such as which would be benefiting from ultra-low latency and high bandwidth, from efficient power use and new levels of privacy. And interestingly, last year, as one of the key trends, Gartner has predicted that by the next year, there will be more than half of all data analysis by deep neural networks at the point of capture, at the edge of the system, right? And considering that just 3 years ago, it was less than 10%. So it's really very powerful trend in the AI domain. And this progress, these fantastic achievements that we are witnessing, the credits for them for sure go to the software community, to the machine learning community, but also I would like to advocate the role of the hardware community. So interestingly, the deep learning was there already for decades. So it was developing, but in 2012, there was such a called renaissance, which kicked off the propelling speed of the development of AI that we are witnessing today. So it happened with AlexNet. It was the first CNN winning ImageNet large-scale visual recognition challenge in 2012. It was developed by Alex Kryzhevsky, a Ukrainian-born Canadian from Toronto University, who proposed a new CNN architecture, which was actually not so much different from the previous architectures, such as LINE by Lee.
Professor Maksim.
Yes.
I don't know if it's your intention to share any slides or not. Are you sharing or not?
Yes, I do.
Yeah, it turns out that our streaming doesn't show any slide. It is still in the title slide. I don't know if the host enable you to share your screen.
Yeah, now you should see my slide, right?
Yes, thanks a lot. Now how many transistors are live is showing up. Thanks a lot.
Okay, so let me repeat this very quickly. So here you can see the computations which were provided by Patrick Gröneveld in the last year regarding the number of grains of sand on all beaches. And there is also a set of computations that he did to compute the number of transistors which are alive as of last year. So in both numbers, they show 60 learn. Then I was also mentioning the trends for artificial intelligence. So there is a chart showing how different disciplines are outperforming human, and the exact trend about HI that I have mentioned. And now we are getting to the slide about AlexNet that was proposed in 2012 by Alex Kryzhevsky, Ukrainian-born Canadian from Toronto University. And again, this CNN, it was not so much different from the existing CNNs, but one of the key points that enabled this CNN to win the challenge was actually the smart mapping of convolutional operators to GPUs. And it's a part of the paper that was published by Alex, and that is collecting a huge number of citations these days, right? So acceleration of AI is crucial, because if we would do the inference of our neural networks just in the processors, then the speed would be probably unacceptable and infeasible for the applications that we would like to see and we would like to use these days. And there are several charts available in the literature which demonstrate the speed up in case if we start to use a specialized hardware for the acceleration, and that the speed up, for example, in case of use of GPUs with single instruction, multiple data architectures can achieve tens of thousands of times compared to the execution in the processor. And this specialization of hardware is relevant because in practice we usually have some specific functions which are necessary, which are actually dominating in the computation for the deep learning. So in case of CNNs and in case of transformers, this is indeed matrix multiplication. So specialized hardware really allows us to speed up this very significantly. And then, interestingly, from our neighboring domain, so not in the machine learning, but in the Bitcoin mining domain, the researchers from the hardware community have demonstrated the opportunities for achieving speed up when different platforms, more general purpose hardware or a little bit more function specific hardware are employed. And then in case of CPU, we can achieve just limited speed ups. And when we move to GPUs, and the speed up can be way higher. And then in case of ASIC-based implementations, we can achieve a huge performance speed up if we focus on the computation of hash functions which are specific for that domain. So something similar we are witnessing in the machine learning domain, where we have this matrix multiplication and similar focused functions. So if we talk about custom DNN accelerator architectures, and if we care about the optimization and the reliability, then we need to keep in mind that there are mainly two types of these architectures. They are usually based on systolic arrays, which are architectures allowing for data to flow synchronously. This architecture is very efficient for matrix multiplications specifically. And yes, indeed, there are numerous architectures which use this approach. And then I see that my camera has disappeared, but I think that's okay. And then there is another type of architecture, which is a data flow. And in this case, actually, we talk about dynamic routing of data. And for each layer, we use a particular set of computing resources, which allows us to have way more optimized use of resources and to adapt to irregular dependencies and a variety of data algorithms. And there are complex architectures such as Iris, MIRI, and also NVIDIA Lay by NVIDIA, which rely on this type of architecture. Okay. Recently, we got approved 2 new European projects with very strong consortia behind these. Both projects will start in September 2024. One of them is a twin project, tight chip, that will last for 3 years. Another one is Tiramisu, Marie Curie doctoral network, which will last for 4 years. And with a consortium of academic partners and also industrial partners, we will focus on development of different AI chip architectures, the optimization and their reliability. So one of the flavors called Combo 1 is here on the slide. So, and such an AI chip architecture can rely on the data which is stored in off-chip memory, and then it can use a RISC-V processor as a main processor for the main part of the application. And for the AI tasks acceleration, we should have a computation core, which would have different types of processing element arrays and dedicated engines, a number of interconnects to orchestrate these data flows, and then a controller which will control the AI core specifically. So that's an example, and everything would be nice and bright and sunny if not the fact that in real life we get hardware faults. So let me try to see if YouTube can actually stream another YouTube video. So let me switch to another window. I hope that you can see it, and hopefully also the dynamics of the picture is nice here. So what you can see here is a video from a cloud chamber. So all these traces are traces of radiation particles. The short, thick ones are alpha particles, and then we also have these tiny ones, and with very curvy trajectories. These are electrons and positrons. So to see all of this, you need a little bit of alcohol. So you evaporate the alcohol and you cool it down so that you have really a cloud. And then what you see on the screen is just normal radiation which is around us. So there is no particular source of radiation. So later on, you can actually check this video from YouTube yourself. And when you see this, and then you realize that any of these particles, any alpha particle or positron or a neutron, they can actually hit one of the billions of transistors on a chip. And then when they do this, they can flip the value, and they can cause a fault in the chip. So that's really scary. So just in case the video didn't play well, I have a couple of screenshots from this video. So these are the thick traces from the particles, and then these are traces of electrons and positrons and neutrons. Okay, and then to study the effect of hardware faults on deep learning acceleration. One of the first papers that was published in this domain was published relatively recently. It was in 2017 by Ali from University of British Columbia and NVIDIA. So this paper is famous because of this picture that is widely reused in our community when a truck is identified like a pigeon. And then a different decision for a self-driving case is made. So it is just an illustration. No bird was harmed for this experiment, but still it's a really scary situation if you rely on artificial intelligence to make decisions. And already in that paper, the authors have demonstrated that the error resilience of DNN systems and the accelerators highly depends on data types, values, types of layers, and the particular implementation of this DNN in hardware. And specifically, they provide experiments where they demonstrate the criticality of faults injected into different positions of the bits, and in case of different data types used. And then a little bit more recent example that was shared on LinkedIn by Professor Pedro Riveriego from Politecnica de Madrid is a case when for generative AI, just a single bit is flipped among billions of bits in the network, and that leads to a very different result of an image generation. And yes, indeed, it shouldn't be an arbitrary bit. Different bits, they have different criticality, and also in that paper, the authors demonstrate that for that particular transformer network, bits at the second position tend to have average value 0. And for example, in this case, what we can witness if we flip these bits, and probably the impact will be one of the strongest. Okay, so in the title of this talk, I say it happens, so stuff happens, and really we need to take it into consideration. We need to do something for the reliability of HAI systems. There is another very nice figure, this time from Alberto Bossio, who actually was also performing in in one of the CASS talks some time ago. So this figure demonstrates the possible locations of faults that we need to consider in DNN hardware. So some of the faults, they can be in the parameters memory. So in the weights and biases, is in the on-chip or off-chip or on-chip memory. And interestingly, if we flip bits in these parameters or biases, then these effects, they accumulate because we keep using the same memory. So if we have single event upsets, soft errors, transient faults, just in the buffers for inputs or for activation or for pooling, then they do not accumulate, but they very quickly start to propagate in the processing array, and also can have a strong impact on the classification output. There can also be faults in the processing elements themselves, or in the control units logic. And in case of FPGAs, we are talking about the configuration memory. And the regions of these faults are also very different, as well as the nature of the faults. So we are talking about aging, electromigration, soft errors, also process variations or manufacturing defects, which are actually happening not during the lifetime of our AI chips, but already during the design and manufacturing, right? And then the effects of these faults, if they're happening, can also be very different. For sure, a large share, most of the faults actually are getting masked for various reasons. So they actually do not propagate until the output, and they do not impact the classification. But there are also faults which can be malignant, which cause silent data corruption, and there can be different types of silent data corruption, like misclassification of the first class, or the predicted of the actual class drops below first 5 predicted classes, etc., etc. But the effect is the most dangerous, because we get a misclassification, and in safety critical system it can be it can lead to very unfortunate results. And some of the faults can be benign. So it means that we have confidence drops. So we say that, yes, we still predict the correct class, but with slightly different confidence. So it is not so dangerous, but in many cases can also be not so much expected and favorable. So I think that it's an intuition that in case of DNNs, there is a very strong intrinsic fault resilience, and it's due to several reasons. First of all, the effect of the effect on the output of a single fault actually is combined with the effect of many other neurons which participate in the computations. Also, DNNs have a probabilistic nature, and the activation functions usually are non-linear, which also leads to be to less sensitivity to small perturbations in the data. So that's at the model level, right? So there is usually quite good fault resilience. But when it goes to the hardware implementing these models and the hardware for accelerating these models, then we have a combination of different effects. So an unfortunate effect here is that one single hardware fault is mapped to numerous neuron computations. So if we have a systolic array, one of the processing elements is faulty, then actually it may be involved in the computation of numerous neurons in the model, and then actually the effect will be much more strong. But a positive side is that actually there is usually a large share of redundancy, and not all the processing elements are, and not all the registers are involved constantly in the inference. And if you get a fault at those locations, then they do not propagate. So consider, as an example, multiplication of a matrix with a vector, and then for this operation, a number of processing elements in a systolic array, they will just stay unused. I asked ChatGPT to generate a picture for the statement that it happens, or stuff happens in an HI chip, and the result was surprisingly very nice. So you can see how ChatGPT sees it. So, but now let's talk about the cost-efficient reliability more specifically. So if we deploy HI for safety-critical applications, then the challenge is not only to have very efficient, resource-wise efficient implementation of these accelerators, because we know that at the edge there are very tight resource constraints. But also we need to consider that the reliability solutions are also very resource efficient. So we need to combine these two constraints. And these days we are talking about very delicate nanotechnology hardware. So based on the analysis of the state of the art and our experience, we would like to outline 6 promising research directions, so which help to achieve cost-efficient reliability for HI. So the first one is analytical and hierarchical reliability and resilience assessment, selective hardening, approximate computing-based trade-offs, so integrated lightweight monitoring and mitigation in the hardware, cross-layer solutions when we consider not just one layer of hardware, but the whole stack of layers in our system. And the last but not least is the in-field health management. So in case if we get a fault, that we manage to live with this fault and to mitigate the effects of this fault in the system. Recently, just in January this year, we have published a systematic literature review on hardware reliability assessment methods for deep neural networks in the ACM computing surveys. And in this survey, we have identified several major methods for reliability assessment. These include fault injection methods, analytical methods, and hybrid methods. And a set of approaches corresponding to this. So for the fault injection, we can do it based on fault simulation, but we can also do it by fault emulation in hardware, or by physical irradiation. We can do this fault injection. And then if we talk about fault simulation, then there is a variety of platforms that can be used for this, and we can either consider hardware-independent fault simulation-based fault injection, or it can be hardware-aware, or we can model hardware in a very precise manner for this analysis. So it can be at RTL, maybe in some cases even at the gate level. And then fault emulation radiation can also target different platforms, mostly those where we also plan to implement our DNN accelerator. And as a result of this analysis, we have concluded that fault injection for sure strongly dominates, and there is a very wide variety of approaches targeting different platforms and then targeting different types of faults and having different types of assumptions. And interestingly, analytical and hybrid approaches, where analytical methods are combined with fault injection ones, are underexplored, while the existing ones were very lightweight and pretty accurate. So this motivated us to proceed with research in this direction. And one of the results is a work published last year at European Test Symposium, is a DFigure, which is a semi-analytical reliability assessment approach. So here, what we can do, so we still stay at the level of a model. We don't consider a particular hardware which is implementing this model. So we can estimate what is the value of fault that we can have at a neuron, such that it will still not impact the classification result by this neural network. So how vulnerable would be this fault or another fault to the classification by this model? And if the added value to the output value of a neuron exceeds some threshold, then we start to get misclassifications. So it can be reflected by vulnerability value ranges. So for each neuron, based on the representative data set, we can compute these vulnerability ranges, saying that if the fault changes output value of the neuron within one range, then nothing will happen. In another range, definitely for any input, there will be an impact on the classification. And also there are some gray areas because in this case we cannot say for certain it can be either a misclassification or not. Right, so the analysis on a representative data set we do only once, and then it works with a very high accuracy from 99 to 100% for any new unseen input, and that is what we can do analytically without any kind of further fault injections. And the basic and the outcome and the effect of these vulnerability value ranges can be represented by vulnerability factors for bits, neurons, and layers. So we can do very efficient analysis of layer vulnerability factors to see how vulnerable would be one or another layer in the network. And if we take neurons in one particular layer of the network, we can sort them by vulnerability, and we can say that there is a number of neurons which are pretty non-vulnerable, so we don't need to protect them, and they have very small influence on the outputs, but there is a range of layers that can be considered, for example, for selective hardening, or they can be considered for whatever other fault tolerance techniques if we have, again, limited resources for our reliability and fault tolerance to be employed. And then as a continuation of that research, we also published work where we apply DFigure exactly for the purpose of selecting neurons which are necessary to be hardened. And as a hardening technique, we used neuron splitting, such that one neuron is represented by two neurons, I mean the critical one, and then it works like this, that the input is halved. So we halve the input, and in case if one of the neurons will get a fault, then the effect of this fault will be mitigated. It will not be so strong. And hopefully it will be then within the range of these non-vulnerable faults and maybe there will be no effect on classification at all. And this approach was demonstrated to be also very efficient. So far so good. We talked about the trends and the background. We talked about the assessment survey, recently published an analytical approach, and then one of the approaches for selective hardening. So not hardening all the network or hardware, but just the particular critical portions of it. So let's move to hierarchical approaches. So that's something that we have published very recently. In this approach, if you would like to have systolic array accurate results, so knowing the effects of faults in the processing elements in the systolic array on the inference of a particular network. So here we do not do the whole simulation of the system only on the systolic array, but we do the simulation until the layer of interest in the model. Then we have this hierarchy, so we lower until the systolic array representation. We do the simulation of this particular layer in the systolic array, and then we lift and we see if the given outputs, if they are modified by the fault in the systolic array, if they propagate until the output, if they will cause misclassification or they will be masked. And in that particular work, which is done in collaboration with École Centrale Lyon and the team of Alberto Bossio, we're also employing a representation of systolic arrays by uniform recurrent equations. It's a pretty old theory dating back to 80s when systolic arrays were used for different purposes, not for DNN acceleration, but then computing the set of equations allows us to simulate the systolic array also in a pretty fast manner. And here we can go even further. So with a deep vigor semi-analytical approach that I have discussed a couple of slides back, we can prune the fault space. So we can say that if fault in a neuron we would not be vulnerable and it would not propagate to the outputs, and we actually can prune this fault, and we don't need to do the lowering to the systolic array level. We can just report this result immediately. And the acceleration that we achieve by combining this set of techniques in this hierarchical fault injection for systolic arrays is in the range of thousands of times. Okay. So one of the promising approaches to achieve cost-efficient reliability at the HI, in the HI hardware, is employing approximate computing. And recently we have published a work which does it in a very unconventional way. So if we think about fault injection by emulation in FPGAs, and there is a very well-known and established tool, FijiFin, which allows us to do this. So we have an implementation of our DNN accelerator in FPGA, where we have a processing system which controls the fault injection, and then we have a programmable logic, our FPGA, and then we have a set of exact computing units, such as multipliers. Then we can do fault injection by emulation, but there is lots of data exchange, and actually there are some delays because we are breaking the pipeline in order to do the fault injection. And what we proposed to do a year ago is to use the errors of approximate computing for good. So if we enable, instead of exact computing units, approximate computing units with the errors caused by approximation, we can harness them such that we will use them as a fault injection. So the advantage of this approach is that we don't actually need to deliver information about a fault, a flip of a value in the FPGA programmable logic. So we don't break the pipeline. So all we need is to activate this approximate unit instead of exact one by just one signal to a multiplexer. And again, this approach allows us to proceed with estimation of the fault resilience of our model and also of the corresponding hardware in a much faster manner. Okay, so very quickly, there is a known trade-off between approximate computing and reliability, and there are several tools which study these effects, and that's something that we also did for the FPGA-based DNA hardware accelerators. So by employing different types of approximate multipliers and in different combination of layers, we can select the optimum combination for the best allocation of the resources, and at the same time keeping fault resilience at the acceptable level. Something which is one of the most interesting approaches we did in the recent years is an approach for employing an adaptive fault-tolerant approximate multiplier in systolic arrays. And the approach works in such a way that we understand that multiplication is the most resource-hungry operation in the processing units. And it's also possible to use the leading one detector in an unconventional manner, and I will explain now how, such that we actually can duplicate the most critical, the most significant bits, the most influential bits in our computation, and to protect them against errors. So that's the overall scheme of this adaptive fault-tolerant multiplier, which currently looks a little bit sophisticated. But this is a picture explains the procedure quite efficiently. So assume that we have 8-bit unsigned data representation for our accelerator. So what we can do, we can prune two least significant bits in this data, and that would play as an approximation of our data, and we would reuse the adders allocated for these bits. We use a particular type of particular implementation of these headers. It's an adaptive header for duplicating computations for the bits which are actually the most significant and most influential in this particular piece of data. And if we have some preceding zeros in the data, then we can actually ignore them. That is why we need this leading one detector. And in case if we have leading one in another position, then we don't actually need to prune any least significant bits. We just shift the data to the left, and then we duplicate duplicate 2 or 3 actually most significant bits, and we achieve very high fault tolerance in this case. So the experimental results demonstrate that compared to the triple model redundancy, which would be the gray bar in these charts, right? The resource utilization is way lower, while the fault tolerance that we achieve with this approach is very comparable with triple model redundancy based approach. And in fact, because we do the truncation of these bits, so actually we get something like approximate multiplier, then the resource utilization is even lower than in the original unprotected exact multiplier, right? And then if we use just an approximate multiplier without this trick for fault tolerances, then definitely the protection would be way lower. So that's the case of the orange bars. Okay, so quickly, one more approach that we use for embedded lightweight monitoring and correction. So here we make use of the fact that very often a number of bits remain unused. So we can use a 16-bit processing unit, but in fact the data that is used for this particular neural network can be just 12 bits, so it can be less bits which are efficiently carrying the data. And then we can build in very lightweight monitors after profiling the data, which would monitor that actually the first bits remain the same, and in case if they are not the same, that they react. So either they notify about the occurrence of the fault through the infrastructure such as the IGTAC network, or they can also apply a very simple mitigation setting the different incorrect bits to zeros, which leads to a very high protection and correction efficiency in this implementation of hardware accelerators. So I would like to briefly touch one more topic, and then we get to the takeaways. So when we talk about complex systems which are employed in industry scale systems for industry scale applications, then we always need to keep in mind that there is a vendor space and user space. So a number of fault tolerance techniques they're already provided by vendors of, let's say, FPGA SoCs, and this can be something like error correcting codes. They can be different types of modular redundancy, lockstep, data scrubbing, etc., which work quite efficiently under particular conditions. And that's something that a user, a researcher or an engineer cannot actually change. It's already in the system, it's already implemented, and we cannot impact it much. But usually it's not enough, and in the user space we still have an opportunity to have fault tolerance techniques and mechanisms that would be more tailored to the application. They could be, in a sense, complementary to the vendor space techniques. And they can provide for much more cost-efficient reliability. And we did an analysis for complex FPGA SoCs, such as AMD Versal SoCs, how well the vendor-provided techniques support fault tolerance in different parts of the system. And the conclusion was that actually there is still lots of opportunities for the user space, because in some cases only a part of the system is protected, or the protection mechanisms are not meant for the harsh environments, such as space applications, or maybe some medical applications. So I don't know, accelerators such as CERN, where you have much higher fluxes of radiation particles, and then, for example, single bit error correcting codes may be not sufficient. Finally, I mentioned health management at the system level and cross-layer approaches. So for this purpose, we also look into a number of research directions. So what is possible to do is to have an infrastructure such as, again, IGTAG based one for exchanging of the error data across the layers of a system, and also to keep in mind the information of the to keep in memory the information of the faults that have been already happening, and to make different types of conclusions, such as maybe it's not a transient fault anymore, but already an intermittent fault because it's repeating at this particular location, and then we need to take an action, we need to isolate this resource, we need to do a remapping based on this information, etc., etc. Okay, so to be more or less in time, let's move to the takeaways. In case of HI applied and deployed for safety critical systems, we need to take care not only about compute efficiency, but also about reliability efficiency. And from the research point of view, there are 6 promising directions that I have mentioned previously. And we have addressed a number of them in our recent research activities. Interestingly, these days, we witness something like a Wild West era of AI. We have a plethora of customized HI chips. So these days, it's pretty easy to make your own HI chip. They can be even generated by artificial intelligence for you, at least the parts of the design. There is very nice access to the open architectures such as RISC-V, and the production of an ASIC became also accessible for not only for large companies, but for smaller companies and even for individuals through the multi-project wafer approaches. And because of this heterogeneity, because of all this very specialized and the diversity of the chips and the architectures, there is a challenge, but maybe also an opportunity for our community, because we actually there is no more kind of one solution fitting all the needs. So the reliability solutions should be also very tailored to the particular architectures and projects. And finally, what we've been also discussing in different occasions, a consolidation of the software and hardware communities is very crucial. So there should be probably some of the conferences, such as Ricardo was mentioning before this talk, where there is a little bit more tighter collaboration of software and hardware communities, such that hardware people would better understand the needs and the trends on the modeling side, and also software community would benefit from the recent solutions in the hardware domain. Okay, so I would like to thank you for attention. So that's our team that was heavily involved in all the research that I presented. We are looking for new people in our team. We have several postdoc and PhD positions open, and all of them, they are related to a number of European and national projects that we have at the moment. Thank you.
Okay, thank you very much, Professor Maksim. This is Sergio Vamp again, hosting the Q&A of the session. I asked all the audience here to feel free to ask and type any questions in the YouTube channel. The streaming went fine. You mentioned the 6 directions of research that you are taking towards having more reliable devices. My question is, which of the 6 you think will provide, with less cost, the largest payoff in terms of reliability? And the second question is regarding how do you see the contribution that will come to reliability from moving into adoption of non-conventional devices, or less non-CMOS convention, like resistive RAM, like magnetic RAM, spin transfers, RAMs, devices which have been under development for the last decades, will they contribute to reliability or may make things even worse? So there are two questions to start off with. Thank you.
Okay, thank you, Sergio. So I don't think there is one particular technique or direction which is kind of the strongest one, the most impactful one. So in fact, it's really very application and architecture and hardware and model dependent, because in many cases, if we have access to manipulating the hardware down to the structure of the multiplier that we involve, then I would say that these different techniques for lightweight monitoring and immediate integrated mitigations, they can be very efficient because they provide for the lowest overhead. But in many cases, we don't have this opportunity. And then if we have a system which is already predefined, or if we need to work with components of the shelf, then cross-layer solutions and in-field health management can be the only way to go, and that's something to be employed. And again, if independent of the implementation technology, if we use a particular type of memory, if we use an emergent technology, very often an analysis and improvements can be done already at the model level. So here we can have fault resilience assessment using analytical approaches and hierarchical approaches. So we can really select the parts of the models that we can manipulate before the implementation. That can help. And then definitely, if we'll have some particular effects, particular faults for the in case of emergent technologies, then we will need to actually provide new solutions at these different levels. So again, if there is a particular structure of our multiplier, so maybe it's something like an in-memory computing, then definitely the lightweight monitoring and mitigation which can be applied there, it should be very, very specific for that implementation.
Okay, thank you. We have been having this 1 hour webinar, very exciting, very enlightful. And I see no more questions from the audience here in the channel. Well, at this point, I would like to thank very much you, Professor Maksim, from Estonia, from Tallin University of Technology, from for your talk to be given to this Rugand do Sul Circuits and Chips chapter. It's been a pleasure and honor, and I hope to see you back in the channel sometime in the future, and also here in South America, where we organize those webinars and the so-called Circuits and Systems talks. Your last words then, Professor Maksim?
Sergio, thank you so much for this opportunity. And yes, it's very easy to reach me by email, so I'm very open for collaboration. Thank you.
Thank you very much. With that, we'll close the transmission. Thank you, all of you, the audience. Please stay tuned to the channel. There are so many talks available. So I hope you had a good journey. Thanks a lot, Professor Maksim, and see you soon.
See you. Bye.